Hi guys, this is the EdExcel A-Level Further Maths, Further Mechanics 1 paper from the sample papers, so let's get straight into it. Question 1. A particle P of mass 0.5 kilograms is moving with velocity 4I plus j meters per second when it receives an impulse of 2I minus j Newton seconds. We have to show that the kinetic energy gained by P as a result of the impulse is 12 joules. Well, to do this question, we would first of all have to use the impulse principle. So, using the impulse momentum principle, which is I equals m times by the difference in the velocities v take away u. We know our impulse is 2I minus j, so we have 2I minus j, and this is equal to m, which is 0.5, multiplied by the change in velocities. Now, of course, we don't know the final velocity, but we know this initial velocity 4I plus j. So maybe if we write this down, we have v minus this u, which is 4I plus j. And therefore, if we do a slight bit of rearranging, you'd find v to equal 8I minus j meters per second. Okay. Now, the kinetic energy, that's given by 1/2 m lots of the magnitude of v squared minus 1/2 m times by the magnitude of u squared. So if we work this out, we have over here 1/2 times by m multiplied by, well, here we have 8 squared plus minus 1 squared. Now, we couldn't square root this and then square again. Either way, we'll end up with this result. And we subtract off 1/2 m lots of 4 squared plus 1 squared. Okay? And if we work this out, you'd find we get 12j. Question 2. We have a particle of mass 5 kilograms, and that's projected with a speed 8 meters per second up a line of greatest slope of a fixed rough inclined plane. The ramp is inclined at an angle alpha to the horizontal, where sine alpha equals 1/7. The particle is projected from the point A on the ramp and comes to instantaneous rest at the point B on the ramp, where AB equals 14 meters. The coefficient of friction between the parcel and the ramp is mu. In a model of the parcel's motion, the parcel is treated as a particle, and we have to use the work energy principle to find the value of mu. Well, if we know that sine alpha is equal to 1/7, from this we can find out what cos alpha is and what tan alpha is. And I've drawn a quick diagram to find out those values. Sine alpha is equal to 1/7. cos alpha is equal to 4 root 3 over 7, and tan alpha is equal to 1 over 4 root 3. And if we draw a quick diagram to illustrate this situation, we've got this situation over here. The particle starts at A, it finishes at B. The distance between A and B is 14 meters. Of course, we've got the weight acting on the particle, that's 5g. We've also got the reaction force. And don't forget, this slope is rough, so we've also got this frictional force, which we also need to include over here. This frictional force is given by F. Okay. Now we can begin by finding out what R is, and then we know that the frictional force F is given by mu R. So having said that, working out what R is equal to 5g times by the cosine of alpha. So we have 5g multiplied by the cosine of alpha, which is 4 root 3 over 7. Okay, and if we work this entire thing out, we get 20g root 3 over 7. Okay, now the frictional force, we can find that out by multiplying mu by R. So we've got the frictional force, which is given by 20g root 3 mu over 7. And now if we use the work energy principle, you should know that the work done is equal to the change in kinetic energy. Okay, so the work done is equal to the change in kinetic energy. So we've got the kinetic energy. Well, the change in kinetic energy, if it comes to rest at the point B, the change in kinetic energy, that's given by 1/2 times by, if you go back, the mass is 5 kilograms, and the initial speed is 8. So we have the loss in kinetic energy is equal to the work against gravity and the work against friction. So we have 1/2 times by 5, that's the mass, times by 8 squared, that's the initial kinetic, that's the initial speed. Then of course we subtract off 1/2 times by 5 times by 0 squared. And the work done, well, the work done against gravity, if it finishes at the point B, we have mgh, and remember we want the perpendicular height, so we have 5g times by 14 sine alpha, and then the work against friction, we have the distance 14 multiplied by the frictional force F. Okay, so let's just label all of this. So we've got the change in kinetic energy, and that's equal to the work against gravity and also the work against friction. So this over here, this change in kinetic energy, is the kinetic energy lost. And using the fact that sine of alpha is equal to 1 over 7, working out these values, on the left hand side we have 160, on the right hand side here we have 5g times by 14 times by 1 over 7. That would be 10g. And then we have over here 14 times by 20g root 3 over 7 multiplied by mu. And remember, we're finding out what mu is. So if we simplify a bit more, we have 160 equals 10g, and here we have 40g root 3 mu, and therefore if we solve for mu, mu is equal to 160 minus 10g over 40g root 3. Okay, so if we work out what the value of mu is, if we grab our calculator, we have over here 160 minus 10 times by 9.8 over 40 times by 9.8 times by root 3. You'd find we get a value of 0.09131, etc. Okay, and now for part B, we have to suggest one way in which the model could be refined to make it more realistic. Well, we have the following. So do not model the parcel as a particle, and therefore we can take into account air resistance. Question 3. A particle of mass m kilograms lies on a smooth horizontal surface. Initially, the particle is at rest at a point O between two fixed parallel vertical walls. The point O is equidistant from the two walls, and the walls are 4 meters apart. At time t equals 0, the particle is projected from O with speed u meters per second in a direction perpendicular to the walls. The coefficient of restitution between the particle and each wall is 3/4. The magnitude of the impulse on the particle due to the first impact with a wall is lambda mu Newton seconds, and we have to find the value of lambda. Well, I've drawn out a quick diagram to indicate what's going on, and going right, I've set that to be positive, and the walls are equidistant, so from the center of the particle to either wall is 2 meters. It starts off with velocity u, and this moves to the right, and then it bounces back with speed v. Okay, so hopefully that makes sense. And now for part A, if we actually use Newton's law of restitution, so let's just write this down. If we use Newton's law of restitution, that states that E is equal to the speed of approach, okay, divided by the, we have the speed of rebound divided by the speed of approach. Okay, so what do we know about this? The speed of rebound, if we take positive to go towards the right, the speed of rebound, that will equal minus v, and the speed of approach, it approaches the wall with u, so we have minus v over u, And we also know from the question that this value of E is equal to 3/4. Okay, and with that information we can therefore rearrange to find the speed of rebound. V is equal to -3/4 multiplied by U meters per second. And we also know that the impulse is equal to mv minus mu. So we have the impulse, which we know already to be lambda mu. So we have lambda mu equals m times by v. So remember, v was -3/4 u. So we have minus m times by 3/4 u. So let's just tidy this up. So we have -3/4 mu, and then we subtract off mu, and hopefully you can see the mu's cancel. Indeed, we are left with a value of lambda to be -7/4. Okay. Now for part B, the particle returns to O, having bounced off each wall once at time t equals 7 seconds, and we have to find the value of U. Now, you have to be a bit careful here. I've drawn out a quick diagram to illustrate what's going on. The particle starts off at the origin, and what essentially is happening is, if you read this entire description, it starts off at the origin and it bounces to this wall on the right. That's the first thing that happens. The next thing that happens, from this wall on the right, the particle goes to the wall on the left. That's the second thing that happens. And then finally, the particle returns to the origin. That's the final thing that happens. Now, what we can do is find out the speed of the particle after the second impact. We already know that E is equal to the speed of rebound over the speed of approach. Now, after the second impact, we can find out the essentially the speed of rebound. Essentially, we already know in the first instance it travels u meters per second. So perhaps if we add this, we have over here u, and then it bounces back, we already know, with 3/4 u. So going this way, we have 3/4 u, and then going back, we can find out what that speed is. So the speed, if we write this entire thing down, the speed of the particle after the second impact and that's the bit in orange which we're working out. We'll call this V dash, and that's equal to E times by V. So you can think of this to be the speed of rebound equals E times by the speed of approach. It's approaching at 3/4 u, and we already know that E on both walls is equal to 3/4. Hence, we have 3/4 multiplied by V, which is 3/4 u. So we get, of course, 9/16 u. So it returns over here to the origin with a speed of 9/16 u. Hopefully that makes sense. And of course the units, we have meters per second. And we also know that time is equal to distance over speed. So let's just write this down. Time we also know to equal distance divided by speed. Okay, so we have the time, we were told that's 7. Now the distance, it's made up of several different parts. Considering the bit in green, we've got 2 meters, that's the distance, and then the speed is u, so we have 2/u. Okay, now going back, the distance is 4 and the speed is 3/4 u. And then it goes back to the origin, the distance is 2 and then the speed is equal to 9/16 u. Okay, and then we can rearrange this to find out what u is. So if we tidy all this up a bit, we have 7 equals 2/u plus 16/3u plus 32/9u. And if we multiply through by 9u on both sides, we have over here 63u equals 2/u times by 9u, which is 18. 16/3u times by 9u, that's 48. 32/9u times by 9u, that's 32. Of course, 63u is equal to 98. In conclusion, u is equal to 14/9 meters per second. Question 4. Figure 1 over here represents the plan view of part of a horizontal flow where AB and BC are perpendicular vertical walls. The flow and the walls are modelled as smooth, so there's no friction. The ball is projected along the floor towards AB with speed u meters per second on a path at an angle of 60 degrees to AB. The ball hits AB and then hits BC. The ball is modelled as a particle and the coefficient of restitution between the ball and the wall AB is 1/√3 and the coefficient of restitution between the ball and the wall BC is the square root of 2/5. For part A, we have to show that using this model, the final kinetic energy of the ball is 35% of the initial kinetic energy of the ball. Well, to do this question, we can first of all look at this diagram and add in a couple of bits in. If this angle is 60, this angle we can call beta, and this angle over here we can call 90 minus beta, and this angle over here we can call this angle gamma. Okay, and we can call this speed over here v and this speed over here v dash, and you've also got the impulses as well. We'll add these in a different colour. We've got the impulse over here. We'll call this I. And then we've also got the impulse over here. If I get rid of this, we've got the impulse over here. We'll call this I dash, okay? And we still have this V over here. And the reason I want to do that will hopefully become obvious during the explanation of this question. Now, if we consider resolving parallel to AB after the first collision, let's just write all this down. So for part A, if we resolve parallel to AB after this first collision, so after first collision, we have over here V times by the cosine of beta equals U times by the cosine of 60. Hopefully that makes sense. This remains unchanged, and therefore you'd find V cos beta equaling U over 2. Okay, hopefully that makes sense. So that's this component over here. Perhaps if we add this in a different colour, this component over here is equal to V cos beta, which is equal to U over 2. And if we now resolve perpendicular to AB after the first collision, resolving perpendicular, let's just write this down. Perpendicular to AB after the first collision, you'd find this over here. V sine beta is equal to E U times by the sine of 60. Okay, hopefully this line makes sense. And we know that E is equal to 1 over the square root of 3. So V times by the sine of beta is equal to 1 over root 3 multiplied by U multiplied by sine 60, which is root 3 over 2. And therefore, hopefully you can see that V sine beta is equal to U over 2 as well. So let's just add this to the diagram. This component over here is equal to V sine beta, which is equal to U over 2. Okay, and now if we resolve parallel to BC now after the second collision, let's just write this down. If we now resolve parallel to BC after the second collision, you'd find over here we have V dash cos gamma. Okay, so remember here we have an angle of gamma and the speed over here V dash, and this is equal to this V cos of 90 minus beta. So that's equal to V times by the cos of 90 minus beta and that of course is equal to V times by the sine of beta, and hopefully resolving parallel to BC you can see why that's the case. So therefore V dash cos gamma is also equal to U over 2. Hence if we add this to the diagram over here, resolving parallel to BC, you'd find here we get V dash cos gamma equaling U over 2. Okay? And now if we resolve perpendicular to BC after the second collision, so now if we resolve perpendicular to BC after the second collision, you'd find over here we have V dash sine gamma, and this is equal to E dash, where E dash over here is equal to this thing over here, the square root of 2 over 5. And we multiply this by V sine of 90 minus beta. So of course resolving perpendicular to BC, we also have this component over here, V cos beta, and that's perpendicular to BC. So we multiply this by V times by the cosine of beta. Okay, so we have V dash sine gamma equals E dash, which is 2 over 5 square rooted, multiplied by V cos beta, which is U over 2, and therefore V dash sine gamma, you'd find this to equal 1 over the square root of 10 multiplied by U. And so if we add this to the diagram, in this direction over here, we have V dash sine gamma equals 1 over the square root of 10 multiplied by U. Okay, so now we've found all the different components of the various velocities. And now remember, in this question we're trying to find the final kinetic energy as a percentage of the initial kinetic energy. And in terms of the initial kinetic energy, if we write this down, the initial kinetic energy, you'd find this to be 1/2 m times by U squared, and the final kinetic energy, that's equal to 1/2 m. And here you have to be a bit careful. We've got different components. We've got this component over here, U over 2, and if we square that, we get U squared over 4, so I'll add that in grey just for clarity. And then we've also got 1/2 m times by U squared, the final kinetic energy squared, so we have 1 over root 10 times by U squared, which is 1 over 10 U squared. So we have over here U squared over 10. And therefore, tidying this up a bit, we have 1/2 m U squared, lots of 1/4 plus 1/10. So we have 1/2 mu squared times by 7/20. Okay? And therefore the fraction of the initial kinetic energy we have over here 1/2 mu squared times by 7/20 over 1/2 mu squared, and then of course we multiply this by 100. These terms cancel out for us. We're left with 7/20 multiplied by 100, which of course is equal to 35%. Okay? And now for part B, in reality the flow on the walls may not be smooth. What effect will the model have had on the calculation of the percentage of kinetic energy remaining? We have the following reason. So this answer from part A, the 35%, that's too large if we have rough surfaces, and that's because rough surfaces means we have more resistance, and that's due to friction, and therefore the final speed will be lower because we've got more resistance. Question 5. A car of mass 600 kilograms is moving along a straight horizontal road. At the instant when the speed of the car is v meters per second, the resistance to the motion of the car is modelled as a force of magnitude 200 plus 2v newtons. The engine of the car is working at a constant rate of 12 kilowatts. And for part A, we have to find the acceleration of the car at the instant when v equals 20. Well, I've drawn a quick diagram to show what's going on. Okay? And what we can do over here is use the fact that the power is equal to the driving force Fd multiplied by the velocity v. So the power, that's 12,000. Remember, we want the power to be in watts, and that's equal to the driving force multiplied by the speed, which is 20, and therefore the driving force pushing forward, that's 600. Okay? And now, using the fact that the sum of the forces is equal to the mass times by the acceleration, taking a look at this diagram, we have the forward force 600 and the resistance force, that's 200 plus 2 times by 20. Remember, over here v is equal to 20, and this is equal to the mass 600 multiplied by the acceleration a. 600a is therefore equal to 360, and therefore you'd find a to equal 0.6 meters per second. And now for part B. Later on, the car is moving up a straight road inclined at an angle theta to the horizontal, where sine of theta is equal to 1/14. At the instant when the speed of the car is v meters per second, the resistance to the motion of the car from non-gravitational forces is modelled as a force of magnitude 200 plus 2v newtons. The engine is again working at a constant rate of 12 kilowatts. At the instant when the car has a speed w meters per second, the car is decelerating at 0.05 meters per second. We have to find the value of w. Well, I think at this point it would be a good idea to sketch out this entire situation. So, having drawn the diagram, of course, we're inclined at an angle theta. We've got this driving force Fd, we've got this resistance force 200 plus 2v. We've got the weight component. Now, again, using P equals Fd times by V, we have over here, if we write this down, we have P equals the driving force times by V. So we know the power, that's still 12,000, and that's equal to the driving force Fd multiplied by V, which is W. And therefore, Fd, you'd find this to equal 12,000 over W. And now again, using the sum of the forces equals the mass times by the acceleration, we know over here our forward force, that's 12,000 over W, and then we've got our resistance, that would be 200 plus 2W, and then we've also got this, the component of the weight, so we have 600 G times by sine theta, and we know that this is equal to minus 600 times by 0.05. And the reason we have a minus over here is because if you go back to the question, it's decelerating. And we can simplify all of this. We know that sine theta is equal to 1 over 14. So we have 12,000 over W minus 200 minus 2W minus 600 G times by 1 over 14. This equals minus 30. And if we multiply through by W and then rearrange, you'd find we have 2W squared plus 590W minus 12,000 hence solving this for W is equal to minus 590 plus minus 590 squared minus 4 lots of 2 lots of minus 12,000. This bit's square rooted, and this bit at the bottom we divide by 2 lots of 2. And therefore, if we solve for W is equal to, if we grab our calculator and go to the equation solver, we have a polynomial of degree 2 with coefficients 2, 590 and minus 12,000. We get 19.1 and minus 314.1. Okay? And therefore, in conclusion, W is equal to 19.1 meters per second. Question 6. A smooth uniform sphere A has mass 2m kilograms and another smooth uniform sphere B with the same radius as A has mass 3 kilograms. And the spheres are moving on a horizontal plane when they collide obliquely. Immediately before the collision, the velocity of A is 3i plus 3j meters per second, and the velocity of B is minus 5i plus 2j meters per second. At the instant of collision, the line joining the centers of the spheres is parallel to I. The coefficient of restitution between the spheres is a quarter, and for part A, we have to find the velocity of B immediately after the collision. I think it's a good idea to begin by sketching out the entire situation, which is what I've done over here. We've got the situation before and after. Before, the spheres are moving on a horizontal plane, and if we consider A, that has velocity 3i plus 3j, and if we consider B, that has velocity minus 5i plus 2j. A has mass 2m kilograms and B has mass 3m kilograms. And afterwards, when they collide, the vertical component perpendicular to the line of center, that doesn't change. So in terms of the velocities, for A we still have 3j, and for B we still have 2j. But we've got these I components of the velocities of A and B, which are v and w respectively. Once we've found those out, we can determine the velocity of A and the velocity of B. Of course, here shown in blue, we've got the impulses upon collision, and here we've got the common tangent. And what we can do for this question is use conservation of momentum. So let's just write this down. If we use conservation of momentum, and if we consider resolving parallel to the line of center, then over here we've got 2m. If we consider the bit before, we've got 2m multiplied by 3. So we have 2m lots of 3 plus 3m, that's for B, lots of minus 5. Remember, because we're considering the conservation of momentum parallel to the line of centers, we only consider the I component, so we have minus 5, and this is equal to the bit afterwards, 2m multiplied by minus v. Obviously you can see why it's minus v, it's going in the opposite direction, and that's of course if we take right as positive. And then we've also got 3m multiplied by w. So you've got this bit over here, which is the bit before, and this is the bit afterwards, and therefore you can see that 3w minus 2v is equal to minus 9. That's if you simplify all this. We'll call this equation 1. And now if we use Newton's law of restitution, so if we use Newton's law of restitution, again if we consider the if we consider this parallel to the lines of centers, remember E is equal to the speed of separation divided by the speed of approach. Okay. And therefore the speed of separation, if we take a look over here, we've got, because they're going in opposite directions, we've got w minus v, which is w plus v. And if we also consider this bit over here, the speed of approach, because they're moving towards each other, we've got 3 minus 5, which is 3 plus 5. And this will equal, if we go back over here, the coefficient of restitution, that's a quarter. So all this over here is equal to 1 over 4. And if we simplify this, v plus w is equal to 2. We'll call this equation 2. And if we solve equation 1 and equation 2 simultaneously, so solving equation 1 and equation 2 simultaneously, you'd find in conclusion W is equal to -1 and V is equal to 3. And therefore, the velocity of A, you'd find this to be 3I plus 3J. And the velocity of B, you'd find this to be -I plus 2J. Okay? And now for part B, we have to find to the nearest degree the size of the angle through which the direction of motion of B is deflected as a result of the collision. So if we work out that angle, I've drawn a quick diagram to illustrate what's going on, what we need to find. We need to find this angle theta, and we can do that by using cos theta equals A dot B over the magnitude of A times by the magnitude of B. So we've got over here cos theta, that's equal to this vector over here, minus 5I plus 2j, dot product with this vector over here, minus I plus 2j, and then we divide this by the magnitude of A, sorry, the magnitude of this vector over here. So we have 5 squared plus 2 squared square rooted, and then we've got the magnitude of this vector over here, minus 1 squared plus 2 squared. So what you'd find over here then, cos theta, we have minus 5 times by minus 1 plus 2 times by 2. On the bottom we've got over here the square root of 29 multiplied by the square root of 5, and if we work this out, you'd find we get a value of well, cos theta, if we work this out, we have 5 plus 4, and then we divide that by the square root of 29 times by the square root of 5. So cos theta is equal to 0.747 etc, and therefore theta, you'd find that to be 41.6 etc to the nearest degree. We have 42 degrees. Okay. Question 7. A particle P of mass m is attached to one end of a light elastic string of natural length A and modulus of elasticity 3 mg. The other end of the string is attached to a fixed point O on a ceiling, and the particle hangs freely in equilibrium at a distance d vertically above O. And for part A, we have to show that d is equal to 4/3 A. Okay, so for part A, I think first of all it will be a good idea to sketch this situation. Hopefully you can see we've got our string hanging from the ceiling. It starts at this point O and it rests in equilibrium. We've got the natural length A, and then of course it extends by some distance x, and of course A plus x is equal to d. Okay, because d is the distance by which d is the distance from the particle to the ceiling. Now, using Hooke's law, Hooke's law tells us that t is equal to lambda lots of x over the natural length, and if we rearrange for the extension, we have x equals t times by the natural length over lambda. Okay, sorry, over lambda. Now we can first of all find the tension, noting that the particle is in equilibrium. So if the particle is in equilibrium, so if P is in equilibrium, then the tension T is equal to mg. That's just resolving vertically. And if we use this information by putting this back into our formula for x is equal to the tension mg times by the natural length, which is a, over the lambda, and lambda, the modulus of elasticity, that's 3mg. And therefore you'd find x to equal a over 3. Okay, and in other words, we know x is equal to a over 3, and therefore d is equal to a plus x. So we have a plus a over 3, which is 4a over 3. That's what we wanted to show. And now for part B, the point A is vertically below A such that OA is equal to 2A. The particle is held rest at A and then released, and it first comes to instantaneous rest at the point B, and we have to find in terms of G the acceleration of P immediately after it is released from rest. Well, again, I think a quick diagram will help illustrate what's going on. So we've got the string which is stretched to the point A, and we've got the length OA equaling 2A, and we can find the acceleration by using F equals ma. Now remember, the sum of the forces, we need to first of all find out what the tension in the string is. And the tension in the string T, that's equal to lambda x over L. So we've got lambda 3mg multiplied by the extension. Now the extension, we've got the string which is stretched to a length 2a, and then we subtract off the natural length a, and then we divide by a. You'd find the tension to equal 3mg. And now if we use the sum of the forces equals mass times by acceleration, we've got T minus mg equals m x double dot. Okay, so we've got T 3mg minus mg equals m x double dot, where of course x double dot is the acceleration, and therefore you'd find the acceleration x double dot to equal 2g meters per second squared. Now for part C, we have to find in terms of g and a the maximum speed attained by P as it moves from A to B. Well, the maximum speed, that occurs when the acceleration equals 0, and the acceleration is equal to 0 when we're in equilibrium. So this occurs when we're in equilibrium. Okay, now we know that the particle is held at rest at the point A and then it's released to the point B, and going from A to B, the maximum would occur at some point Q. Okay, and I think drawing out this situation would help. So hopefully you can see over here that the particle starts at the point A and it goes to the point B, and I've shown that in blue over here, and the max speed would occur at this point Q over here, and over here this is where the particle is in equilibrium. So let's just put that down into words. The max speed occurs at the equilibrium position and that is when A is equal to 0. Now the elastic potential energy, that's equal to the work done to stretch the spring. Okay, so the elastic potential energy is equal to the work done to stretch a spring. So if we use that, we've got the elastic potential energy at this point A. You'd find that to equal 3 mg times by 2a minus a over 2a. Hopefully you can recognize that's lambda times by let me square this, so hopefully you can recognize this is what do you call it, lambda x squared over 2l, and this is equal to, again, the elastic potential energy at this point B. So sorry, at this point Q over here, we're considering over here on the right hand side everything on the point Q, so we have 3 mg multiplied by the extension a over 3, and we square this, and we then divide by 2a. And the reason we have a over 3, if we go back to a previous diagram looking at the equilibrium position over here, perhaps if we call this point over here Q, hopefully that makes more sense. And then at this point also we've got the kinetic energy which we're concerned with, 1/2 mv squared, and then we've also got the gravitational potential energy at this point Q. So we have mgh, so we have mg times by, well, we have the height over here. If we label this in a different color, this over here, this height over here, this is equal to 2a minus 4a over 3. Okay, so we have 2a minus 4/3 a, and everything on this right hand side is what we have at Q. So perhaps if we show this clearly, we have everything on the left hand side which is at the point A, and then everything on the right hand side which is at the point Q. And if we simplify all this, you'd find we have 1/2 v squared equals 2/3 ga, and therefore v is equal to 4ga over 3 square rooted meters per second. So this over here is the maximum speed. And now for part D, we have to find, in terms of A, the distance OB. Well, we know that at the point B, the particle comes to rest, so therefore we can say over here that the kinetic energy at the point B is equal to 0. and here is when we have the maximum height. Perhaps if I add this to the diagram, we've got this height over here, which is what we're concerned with. Okay, and if we call this h over here, then we can find OB by subtracting OA from h. Subtracting h from OA. Okay, so we know that over here we've got a length of 2A. Okay, so we know that if we write this down, we know that the particle comes to rest at this point B, and hence at the max height h, at this max height h, the kinetic energy is equal to 0. We just discussed that, and therefore the elastic potential energy that we've lost from the point A, this is equal to the gravitational potential energy that we've gained at B. Okay, hence the elastic potential energy at A, if we use what we have over here, that's 3 mg A squared over 2A, and then this is equal to mgh, and therefore hopefully you can recognize that h is equal to 3A over 2, and therefore the length OB, you'd find this to equal 2A minus 3A over 2. Of course OB is equal to A over 2. Question 8. A particle P of mass 2m and particle Q of mass 5m are moving along the same straight line on a smooth horizontal plane. They are moving in opposite directions towards each other and collide directly. Immediately before the collision, the speed of P is 2u and the speed of Q is u. And then the direction of motion Q is reversed by the collision, and the coefficient of restitution between P and Q is E. We have to find the range of possible values of E. Well, they're moving along a straight line and they're moving towards each other in opposite directions, and the speed of P before is 2u and the speed of Q before is u. So I've got the particles P and Q drawn out over here. They're moving towards each other. So here we've got 2u, and then here we've got u. This is the situation before. After, when they collide, the direction of Q is reversed by the collision. Okay? Well, for now, before we do anything, let's just give these arbitrary values. We've got W over here. Sorry, we've got V over here and we've got W over here, because obviously the reason for this situation afterwards is obviously when they collide, they're going to be moving in different directions once they've collided. Okay, they're going to be moving in opposite directions when they collide. That's a bit obvious. Okay, hence we've got the arrows pointing in opposite directions with the situation afterwards. Now if we consider the conservation of momentum, so using conservation of momentum, we've got, if we consider particle P before, we've got 2m multiplied by 2u, And then we've also got Q. Sorry, this is of mass 5m. It's of mass 5m. We've got 5m multiplied by minus u, because it's going in the opposite direction. And afterwards, if we consider P, we've got 2m, lots of minus w, and then we've got 5m, lots of v. Okay, so this over here is the situation before. Perhaps if we put this in red. So this over here is the situation before, and then here is the situation after. And therefore, simplifying all this, you'd find minus u is equal to 5v minus 2w. We'll call this equation 1. And now if we use Newton's law of restitution, okay, so now using Newton's law of restitution, we've got E, which is equal to the speed of separation divided by the speed of approach. Okay. And therefore, we know that the coefficient of restitution is E. So we have over here E, which is equal to V plus W. Okay, and that's the speed at which they're separating. So if you go back to the diagram, you can see the speed at which they're separating is V minus W, which is V plus W, and they're approaching towards each other at 2u plus u. And therefore you can see over here 3eu is equal to V plus W. We'll call this equation 2. So if we solve equation 1 and 2 to find simultaneously to find the speed of V, we can then use the fact that Q is reversed to set an inequality. That's to say V is greater than 0. So if we now solve equation 1 and equation 2 simultaneously to find V, then we have equation 1, which is minus u equals 5v minus 2w. Equation 2, that was 3eu equals v plus w. And if we multiply this equation by 2 to get the w's the same, to cancel out the w's, we see that we have 6eu equals 2v plus 2w. And if we now add equation 1 and equation 3, you'd find we have 7v, because we have 5v plus 2v, and this is equal to 6eu minus u, and if you factorize out a u, we have u lots of 6e minus 1, and therefore v is equal to u over 7 lots of 6e minus 1. And then we know that the direction of motion of Q is reversed by the collision. So in other words, V is greater than 0. Okay. Because it's going to be opposite to what this W is. Okay. So using the fact that V is greater than 0, we have u over 7 lots of 6e minus 1 is greater than 0, from which we see if we divide through by u over 7, we see that 6e minus 1 is greater than 0, and therefore E is greater than 1/6. And we know that E must lie between 0 and 1. Okay, and therefore the range of values for E, we have 1/6, which is less than E, which is less than or equal to 1. And now for part B, we have to show that the kinetic energy lost in the collision is 40 mu squared over 7. Well, now that we know that E is equal to 1/3, we can use this to find out what V is, and we can also use that to find out what W is, and those will be the speeds of well, if we can make sense of this. We know the speeds before, so we can find the kinetic energy before, and if we know what V is and what W is, both in terms of U, then we can find out the kinetic energy lost. So when E is equal to 1/3, we have V, which is equal to U over 7 times by 6 times by 1/3 minus 1. That's U over 7. And knowing that V is equal to U over 7, we can substitute this back into equation 2 to find out what W is. So when E is equal to 1/3 and V is equal to U over 7, using equation 2, we have 3 times by 1/3 times by U, and that's equal to U over 7 plus W. W therefore is equal to 6U over 7. And therefore, the kinetic energy lost, well, before, if you go back over here in red, we have a half times by 2m times by 2u all squared, and then we also have a half times by 5m times by u squared. So before we have 1/2 times by 2m times by 4u squared plus 1/2 times by 5m times by u squared. So this is the situation before. And then afterwards, because we've got kinetic energy lost, we subtract 1/2 times by 2m. Now we've got over here, if we consider P, we've got over here W, and remember W was equal to 6u over 7, so squaring that, we got 36u squared over 49, and then we've also got 1/2 times by 5m times by V, which was u over 7, so we've got u squared over 49. So this is the situation that occurs after. And therefore, if we simplify all this, the kinetic energy lost, that's 40 mu squared over 7. And now for part C, without doing any further calculations, state how the amount of kinetic energy lost in the collision would change if E is greater than 1/3. So if E increases, the particle becomes more elastic, so less energy is lost in the collision because it's sort of stuck more together, if that makes sense. Okay?